Mark is tired after a long day of work and plans on commuting back home to relax. But there is a problem. To get back home, Mark must first cover half the distance to his home, then half the remaining distance, then half of what's left, and so on. Thus, getting home requires completing an infinite amount of subtasks, which could take an infinite amount of time. Is Mark hopelessly stuck at work? In this video, I want to explore the concept of infinity and tackle some of its mind-bending properties head-on. In doing so, we will explore some of its apparent paradoxes and mysteries and emerge with a more nuanced understanding of its complexity. The problem that I just proposed is essentially a rephrased version of one of Zeno's paradoxes, a set of apparent logical inconsistencies proposed by Zeno of Elea from the time of ancient Greece. These paradoxes sparked much debate. Legend has it that one of Zeno's contemporaries, Diogenes, reacted to this supposed movement paradox by simply standing up and walking around, as if saying, "Take that, Zeno." Unfortunately, such a demonstration only further elucidates the issue at the heart of the paradox. Let's look at a more concrete resolution to the problem. Let us denote the distance that Mark needs to cover to get back home as x. Then, the individual steps that Mark has to take are of length 1/2 x, 1/4 x, 1/8 x, and so on. Let's now say that Mark is capable of traveling at a speed v towards his house. Now, recall that the time taken to travel a certain distance is equal to the magnitude of that distance to be covered over the speed at which it is traversed. The line segments that we have labeled here are all distances, so we can divide each by the speed v to get the time taken by Mark to complete each stage of his journey. Adding up all of these times should give us the total time needed for Mark to get back home and will allow us to check if it is really impossible for him to return. The equation for total time involves an infinite sum. We can clean the summation up a bit by factoring out the factor of x over v that is common to all terms. The part in brackets can be seen to be a sum of quantities that decrease by a factor of 1/2 between subsequent terms starting from 1/2 itself. This kind of constant ratio between terms defines a geometric series, and these can be summed in a multitude of ways. In this case, the easiest way to sum this geometric series is actually by using a picture. Consider this square of side length 1. Imagine shading in half of the area of the square, then shading in half of what's left, then shading in half of what's left again. If we repeat this process to infinity, one would notice that the entire area of the square becomes shaded. This diagram represents the same geometric series that we were discussing visually. The sum of this series is simply the area of the entire square, which is 1 times 1, or just 1. If we substitute this result back into the expression for the total time, then we get a quick simplification down to x over v as the time that it will take Mark to get home. Let's interpret this result. X is the distance that Mark needs to travel to get back home, while v was his travel speed. These are both finite quantities, so the total time that it takes for Mark to get back home is finite, resolving the paradox. Thus, this infinite set of tasks can be completed in a finite time. We can understand this result intuitively by noting that although there are an infinite number of segments of the journey back home that Mark must complete, each successive segment takes an amount of time that decreases at a fast enough rate that ensures that the total time is finite. Although this may appear novel, this notion of infinity is something that we've all played with since elementary school. Consider the innocent fraction 1/3, which as a decimal is 0.333 repeating. If you think about what it actually means for 1/3 to be equivalent to this decimal expansion, then it is that I can write 1/3 as the sum of 3/10, 3/100, 3/1000, and so on. This is an infinite series, with a form not dissimilar from that which we observed earlier. So it turns out that we've been dealing with infinite sums for a long time now. As As a fun little side note, notice what happens when I take the original expression for 1/3 and multiply both sides by 3. If I do the multiplication on the left side of the equation, I clearly get 1, as the numerator and the denominator here cancel. On the right side, I multiply 3 times each of the decimal digits of this infinite fraction, getting 0.999 repeating. Thus, 1 and 0.999 repeating are actually equal. This seems impossible, but this is just one of the interesting phenomena that occur at infinity. One way to try to conceptualize this intuitively is that there is no number that you can insert between 0.9 repeating and 1, so they must be equal. Yet, the oddness of infinity does not end here. Imagine that you're playing a lottery where there's an infinite number of tickets. You buy one ticket, hoping that you'll be the lucky winner. What is the probability that you win the lottery? In some problems like this one, it's not always obvious how to start. In such cases, it can be helpful to implement a general problem-solving strategy. Try a simpler version of the problem. In this case, while it may be hard to find the success probability with an infinite number of tickets, it is easy in the case where there are, say, only 2 tickets. Here, you own one of the 2 tickets, so the probability of winning is simply 1/2, or 1/2. Yet, there's nothing particularly special about the number 2. Similar logic would apply for 3 tickets, 4 tickets, or any other finite number of tickets, x. How does this abstraction help us? Well, we can notice that the probability of a success if there is an infinite number of tickets present is simply the limit as x approaches infinity of the probability in the finite case. Thus, this probability is the limit as x approaches infinity of 1/x. Evaluating this, we get the surprising answer of 0. This means that the probability of any one ticket winning the lottery of an infinite number of tickets is 0. This seems to imply that it's impossible for any single ticket to win, but this isn't true either, as one ticket must win, as it will be drawn. This classic example illustrates that probabilities of singular events occurring become almost meaningless when an infinite number of outcomes can occur, which is why mathematicians usually choose to study groupings of events instead. However, now that we've stepped firmly into the realm of calculus, let's look at other related paradoxes at infinity. Consider the following solid formed after rotating the graph of y equals 1/x over the x-axis between the x values 1 to infinity. What is the volume of this solid? Well, the volume of this shape can be found simply by using the disk method, which states that this volume should be given by pi times the integral of y squared dx. In this case, y equals 1/x, and the bounds of our integral should be the same as that of our region, or 1 to infinity. Evaluating this integral involves taking a limit and finding the antiderivative of 1/x squared, which is just negative 1/x. But when the dust settles, we simply get the answer of pi as the volume of this solid. Consequently, this infinitely long solid has a finite volume. While this may not be much of a surprise given what we've already seen with infinite series converging to finite numbers, this puzzle has only just begun. Since we've gone ahead and found the volume of this solid already, let's do a little more exploration and try to find its surface area. In this case, we can pull out the surface area formula to tackle this challenge, which states the following. Making all necessary substitutions for the specific functions and values in this problem, we find the following integral to define the area in question. Simplifying, we rewrite the integral into this form. While this integral itself is quite challenging to evaluate, we can observe that its value must be greater than the integral over the same bounds of 1/x, as the constant factor in front and the terms under the square root are all greater than 1. The integral on the right can be shown to diverge as its antiderivative is the natural logarithm function, which goes to infinity in its end behavior. Therefore, the original integral for the surface area of this solid must also diverge. In other words, this solid has a finite volume, but an infinite surface area. This seems impossible. Consider, the statement seems to imply that one could fill this solid with a finite amount of paint, which would subsequently be sufficient to paint the inside of the solid. However, as the solid has no thickness, this appears to suggest that a finite amount of paint should also be able to paint the outside surface as well, making the surface area finite. Yet, this paradox can be quickly resolved by being more careful in defining what paint really is. If we say that the paint is somehow ideal and infinitely thin, then it does not follow that the calculation for an infinite amount of surface area would imply the requirement for an infinite volume of paint, as infinite area times zero thickness is an indeterminate form of a limit. On the other hand, if the paint has finite thickness, then painting the outside of the solid could still necessitate an infinite amount of paint, as painting the inside of the solid and outside of the solid become two different tasks. Thus, with some careful reasoning, this apparent paradox is resolved in both cases. I shall leave you all with one final tidbit. Any finite line segment has the same number of points on it as a line of infinite width. Don't believe it? Fair enough. Consider an arbitrary line segment like this one. I can bend this line segment into a semicircle without changing its length. Now, consider this line of infinite length. It turns out that every unique point on this finite semicircle can be projected to a unique point on the line. This can be demonstrated from the following transformation. Consider the point at the center of the semicircle and an arbitrary point on its perimeter. A line can be drawn passing between these 2 points and one on the red line. Notice how through this line, each point we choose on the semicircle is associated with exactly 1 point on the red line. This one-to-one correspondence implies that the set of points on this finite line segment is the same as that in the infinite line, concluding this proof. In this video, we explore the concept of infinity, from basic decimals to integral calculus. Along the way, we've been intrigued by its mystique and overcome its paradoxes, ultimately being left with only a greater curiosity of its infinite wonder. If you enjoyed this video, please consider supporting the channel by subscribing. Nevertheless, I hope you have a good day, and I'll see you all next time.